Ladies and gentlemen, can you hear me okay? This is a strange microphone. It doesn't amplify in this room, so I have to speak up. But apparently it's necessary because this presentation is being recorded, and in order for what we say to be incorporated into the recording, I have to use this microphone. Joanne is also mic'd up, and she's going directly as far as I know. Anyway, my name is John Thompson. I'm the Associate Vice President of Research here at Waterloo, and it's my pleasure to welcome you to the first Research Talks session of 2017, brand new year. The beginning of a new year is a great time for a lot of things. It's a great time to highlight some of the transformational research that's underway at the University of Waterloo, especially as we begin to celebrate 60 years of innovation and research excellence at UW. We've come a long way, I think it's fair to say, since 1957, when 74 students began their studies here. Actually. Now, Waterloo research, innovations, technologies are literally changing lives around the world. Research Talks is an ongoing series of lectures given by UW faculty that is organized by the President's Office and the Office of Research jointly. And it's also financially supported by the Research Support Fund. The lectures are designed to bring together faculty members, staff members, and students to learn more about the research that's being conducted at the University of Waterloo and to take part in discussion of this research. And our speaker today is Joanne Attlee, a professor in the Sheridan School of Computer Science and the first director of Women in Computer Science, a group dedicated to promoting women studying and pursuing careers in computing. Joanne received a Bachelor of Computer Science and Physics degree from the College of William and Mary in the United States, and she received a master's degree and a PhD degree, both in computer science from the University of Maryland. She is, simply put, internationally renowned for her research. She has given keynote addresses at prestigious conferences around the world, including the IEEE International Requirements Engineering Conference and the International Conference on Modularity. Joanne serves on several editorial boards, including the IEEE Transactions on Software Engineering, Software and Systems Modeling, and the Requirements Engineering Journal, and previously served as vice chair of the International Federation for Information Processing, an international group of researchers working on advances in software requirements engineering. In November of last year, 2016, she was recognized as a distinguished member of the Association for Computing Machinery for her contributions to the field of computer science. Joanne's research focuses on software modeling, documentation, and analysis. She's perhaps best known for her work on model checking software requirement specifications, and her work has involved collaborations with major international companies around the world, including AT&T, IBM, and GM. Other research interests include model-based software engineering, modular software development, feature interactions, and cost-benefit analysis of formal software development techniques. Joanne is a math faculty advocate for the He-for-She Impact 10 by 10 by 10 campaign, and a long-time advocate for increased female participation in her field. Joanne, I now invite you to give your lecture.
Wow. Well, thank you for that very warm introduction, and thank you for the invitation to speak today. So I'm going to talk a little bit about the research that we're doing here at Waterloo in the WATFORM group on detecting detecting errors and improving software quality. So I probably don't have to do a lot of motivation and tell you that software is buggy. If you look at the news these days, you can pretty well, it's not uncommon to find stories and headlines about some major error in a large piece of software that affects lots of different people. And in fact, whenever I talk about buggy software, I can pretty well rely on there being some recent story in the news that I can put on the slide. And Air Canada came through for me, although Air Canada doesn't have bugs, they have glitches. So, and keep in mind, these are just the errors that make headlines, right? We deal with software errors all the time in the software that we use every day, in the appliances that we have in our homes, the work packages that we're using at work. And some of our local favorites, Quest, which is probably a lot more stable now than it was in the beginning. But if you want to hear some really good stories about Quest, you should seek out David Taylor. He was Associate Dean of Undergraduate Studies when it came into being, and it was a huge feat to actually turn PeopleSoft employment software into a student information system. JobMine, which has been replaced, so Learn, it tends to be quite buggy just because it's being constantly updated, and the updates are often have bugs in them. 4 is practically unusable. And my current favorite is Concur. Okay, so who should we be blaming for all of these errors, right? Is it the software developers? You know, is software being developed by incompetent, negligent developers? Is the skill shortage so short that they're simply not being developed by experts? Or is there something inherently difficult about writing correct software? Well, I would say yes to both, right? So it's certainly the case that some software errors can be attributed to either incompetence or negligence. But I would also say that really good software developers write buggy software, right? And they write software that has lots of errors in it. So I guess I'd at least initially talk a little bit about, you know, the inherent limits on software correctness. So that we've always, like the scientific community has always talked about, you know, how can we improve the quality of software? But in the mid-'80s, when the software community started to actually develop safety critical systems, software in medical devices, or what you have here is the US military wanting to create an automated missile defense system. Now you're talking about software where an error could actually have really catastrophic consequences in terms of loss of life or loss of significant property. And so that's when the scientific community started really looking at, well, what is our ability really to write reliable software? And so that's been a focus of research for a good, 35 years now. So you know, why are we limited in our ability to write perfect software? Okay, well, for one thing, it is generally impossible to thoroughly test software. So even if I gave you a very small program, this is the only code that you're going to have to read today. Very small program, 4 lines long. It computes the greatest common divisor of 2 integers. Now, if you think back to your grade school days and trying to figure out the greatest common divisor of 2 integers, what you probably did was, you know, use a little bit of memory, use a little bit of intuition, make some guesses, make some hypotheses, and then test your hypotheses. Well, you can't do that with a computer. With a computer, you actually have to give it a recipe, right? A step-by-step algorithm for computing greatest common divisor. Okay, so I got an algorithm from the internet. Okay, so maybe I don't trust it. And the algorithm isn't obviously correct, and so we should test this to see whether it is actually going to give us the correct results. So if you wanted to test this for all possible inputs, if you really wanted to be thorough about it, you would be running how many tests? 1,000 times 1,000. 1,000,000 tests. Okay, doable. right? But doesn't really scale to large software systems. So if we were to take this approach of testing all possible inputs and apply it to something large like Quest, right, we're never going to test all possible inputs, right? All possible, information about students, information about courses, information about marks, financial data. It's not going to happen. Okay, so we can't thoroughly test our software on all possible inputs. Right, and so the obvious strategy is, well, let's test it on a few inputs and assume that that's gonna, we can infer correctness of the untested inputs. And the interesting thing about software is that it has what we call discontinuous behavior. So if I look at hardware, if I look at an engineered physical system, if I look at a bridge and I want to know how much weight a bridge can hold, well, I can test different weights of whether the bridge can hold that weight, and I can infer about how the bridge is going to behave on any of the intervening weights that I haven't tested it on. Right? If it holds for 100 pounds and it's going to holds for 1,000 pounds, I can pretty well be guaranteed that it's going to hold for weights in between. And if I'm driving a car and I push the accelerator halfway and the car goes so fast, and I push it 3/4 of the way down, and the car goes so much faster, I can pretty well guess how the car is going to behave in intervening pressures of the accelerator. Well, this kind of continuous behavior is not true of software. Software has a lot of conditions that cause the software execution to go on very different paths through a program. So even if you take two inputs that are very close together, let's say input of two integers, 100 and 100. What is the greatest common divisor of 100 and 100? Well, it's 100, and there's a very simple path through this program. We deviate from the inputs by 1, ask what the greatest common divisor of 100 and 101 is, and we get a very different behavior in the sense that the algorithm's going to have to loop through multiple iterations before it finally settles on 1 being the result, right? So we've got two slightly different inputs. They not only have drastically results, but they take very different paths through the program. Okay, and so these days when we talk about testing, we no longer think about testing software in terms of trying to get any sense of guarantee that the software is correct. Testing is really all about finding bugs. And a good test case is a test case that reveals a bug, because that actually tells us something about the software. A test case that passes doesn't really tell us anything, just because it tells us that it passes that one path, but doesn't necessarily tell us about other paths through the software. Okay, so an interesting type of software problem is integration problems, right? So despite what I just told you about the impossibility of writing error-free software, we're actually pretty good at writing small programs. And so a strategy of tackling a large software system is to decompose it into small problems, which you then solve individually, and then you put the pieces together again for a program. Okay, well, putting the pieces together again is not as easy as it sounds, right? In the same way, if you were to write a large report for work, you would not sit down and write it from beginning to end, right? You would break it down into pieces. You might tackle different pieces on different days. You might delegate some of the tasks to others. And then when it comes to putting the pieces together, you're not going to staple them together and hand it in as your report, right? You're gonna see that once you see all the pieces together, maybe you want to structure which text goes into which section so that the flow of information is a little better. Some of the sections should probably have references to other sections, so you need to insert those. And you're going to see that the consistency of the writing is right. So the writing is inconsistent, right? And so you're going to have to do some revision of the overall writing. So the same thing happens with software, right? We can put these pieces, we can write these individual pieces, but the actual stitching of the pieces together takes a surprising amount of time. It's so surprising that it surprises the software developers. When software developers are asked to estimate how much time it takes to develop their software, once they're about 50% done, they tend to think they're about 90 to 95% done. And they think that for the rest of the duration of the project. And so some of that is optimism about, about errors in the code and testing. But a lot of it is this notion of we've written all the pieces of code. All we have to do is stitch them together. and the stitching takes quite a bit of time and effort. A fourth factor is a poor understanding of the operating environment of the software system. Okay, so we've got software, some software systems monitor their environment or control their environment, right? So medical devices will monitor patients' conditions and they might control aspects of patients' vitality. We've got information systems that, or simulation systems that try to have an internal model of their environment in order to make recommendations about for their users. Okay, so if that software has an incorrect model of its environment, then it's going to be making wrong decisions about how it should react to input. And so a very famous case there, a very expensive case, was the Denver Airport automated baggage system. Okay, so when the Denver Airport opened, they intended to have a completely automated baggage system. But they were having trouble understanding the physics of the baggages and understanding the physics of the airflow in the system. So they weren't really sure, how often they ought to have sensors and how often they ought to be sensing the environment. They were making incorrect assumptions about the sizes and weights of the baggage. So you had bags flying off the carousels when it went around corners. The carts that were driving automatically were crashing into each other. Bags were jamming the system. This baggage system delayed the opening of the airport by 16 months at $1 million a day. And then when it did open, it was only partially automated. It was only working for 1 out of 3 carousels. It was only working for outbound flights, not for inbound flights. And it was so expensive and so buggy still that they eventually terminated it, right? Huge expense, never really got working. And in fact, a lot of what the Google car is doing in its driving around, it is testing its software, but it's also collecting information about its environment to build a better world model of its execution environment. Okay, so what do I mean by that? Well, there's 2 types of information it's collecting. The first type is it's collecting very precise information about the roads that it's driving on, right? So where are the lane markers? Where are the curbs? How high are the curbs? Where are the traffic lights? How high are they? Right? The intent is to create as precise a model of the empty world that it's going to be driving in, so that when it is driving in it, all it has to do is focus on the difference between what it's seeing in terms of obstacles and objects and pedestrians and cyclists versus what it expects to see in terms of the actual roadway. Okay, so it's going around and it's collecting information about the streets. Note that what this means is that the autonomous vehicle is only ever going to be able to drive in places where it has already done this mapping. right? You're not going to be able to pick up the car that's been learning how to drive in Silicon Valley and move it to Cincinnati, Ohio, and drive. The other thing that they're doing is they are learning the behaviors of dynamic objects in their environment. So how do cyclists behave? How do humans behave? How do other cars behave? So this data they take back to the lab, and they use machine learning, deep learning, to build a model of expected behavior of these objects. So that again, during driving, they can focus on deviations from what they're expecting, but otherwise know how to behave on the road with other cyclists, other cars. So they've driven about 2 million miles now, and they have collected a lot of behavior. They've collected some really unusual behavior. To give you a little bit of an idea of some of the unusual things that they've seen, I've got a small clip from a keynote at the South by Southwest conference last year. This is by Chris Urmson, who's the director of the Google Self-Car project. So I'm going to try to make this work. So just as an aside, I didn't mean to be demonstrating buggy software in this talk, but I am running a YouTube. I'm running a YouTube video, which is a Google service, inside PowerPoint, which is a Microsoft product, on an Apple machine connected to I don't know what kind of a data projector. And it doesn't actually work, except that there is a workaround, I think. So bear with me as I move out of presenter view mode. And now I should be able to start the video. So as you can see, so some of the video is the speaker. Some of the video is visualizations of the kind of data that Google collects on these drives. And so you can see that on the backdrop of the simulation is the precise street mapping that has already been done, right? And that the car is working with. And all the car really has to do is figure out deviations from this precise mapping. Okay, and what are the deviations? The blue objects are cyclists for the most part. Yellow objects are pedestrians. And purple and green objects are vehicles. And usually in some of these simulations or visualizations, there's a part of the visualization that shows you what the camera is actually seeing. Okay. I hope this works.
Now, something, of course, the weirdest things we've seen on the road. Over a year and a half ago, our car was in Mount View and did this. Came around a corner, and what you look at here, the duck, and we're in an electric wheelchair with a broom.
So sorry, I think people are using the internet in here, so I don't have precise streaming. That's a duck and a woman in a wheelchair with a broom chasing the duck.
Job is to come up with weird stuff. With this,
okay.
And I go to the DP handbook.
So I don't know whether we can see much of him because of the streaming problems, we're not able to do that. But just to give you a little bit, one other
thing we see on the road. Well, I was wrong. So since then, we've seen people hook Frogger with the car. And honestly, Austin kind of takes the cake. So here, we're in a section that 1, 2, and wait for it. That's 3 cars going the wrong way down the road, all at once. That was fantastic.
So the vehicle, tries to take this information. It recognizes that these are anomalies, so it's not going to build this into their model, but it tries to build a model of how these dynamic objects are supposed to behave. And then when it sees a deviation, the behavior of the car is effectively to stop and wait for whatever the scenario is to play out, and then it moves on. Okay, so those are some of the reasons why we've got buggy software. And just how buggy is the software? Well, a good industrial standard software process is going to leave about 1 to 10 lines of residual errors in the software. And what a residual error is one that is actually going to be experienced by users. So about 10 times of that are what are called latent errors. These are defects. They are in the software. They could actually be realized, but for one reason or another, they're not ever realized. About 1 to 10 lines per 1,000 line of code is residual errors. Okay, so if you've got a 1,000,000-line program and we're really generous, and so there's only one error defect per 1,000 lines of code. And we've also known that the severity of errors tends to drop off, again, in orders of magnitude. So 90% of residual errors are going to be fairly innocuous. About 1% are going to be like mission critical. So if you've got 1,000,000 lines of code, you've got a good 10 errors in there that are going to be experienced, likely to be experienced, and are mission critical. If you've got an autonomous vehicle of 100 million lines of code, and it's developed by good industry standard practices, you're looking at about 1,000 possible 1,000 severe errors in the software. How can we do much better? Well, NASA tends to be looked at as the very best software processes, right? They tend not to use problematic library software. They have very good coding standards. They have manual reviews of all of their artifacts. They do a significant amount of testing. They do a significant amount of automated analysis. They do mathematical verification. They get an order of magnitude better defect rate, right? So it's really not realistic right now with current technology to believe that we can write error-free code. Okay, so what are we doing? Our group looks at a particular type of error called feature interactions. And so it's an integration error, right? Where you've got pieces of software, they work correctly in isolation, but they don't work when you put them together. Okay, so first of all, what is a feature? So a feature is a unit of functionality. And normally features tend to have observable functionality, observable capabilities. Users and customers will often have, will know the names of these features. Right, so a feature is a nice way of decomposing the software into parts where each part is some function, right? So in Word, it can be watermarks or spell checking, and features in Word tend to be just part of the product. And different releases will add to the set of features that are available. In other domains, there'll be some basic service, and you, the user, get to pay if you want access to additional features. Okay, so customers like features, users like features, right? It helps them to evaluate software. It helps them to compare software. They'll often choose one software package over another because of the features that it offers. Companies like features because it makes it easy for them to customize software for different market segments, right? So you can offer some basic service for a lower price, but anybody who wants additional functionality, additional capabilities, you can charge them for either for that feature or for subscription or even per use for that feature. Okay, and developers, right? Engineers like features because it is a nice way of decomposing a problem into pieces, right? You can think about their individual work task. It's a coherent problem that they can get their heads around. Many of them tend to be on the relatively manageable size. They can write it correctly. They can test it. And all of that is fine until they go to stitching, like I said, stitching the features together, right? So this is where the integration problem comes in. And so these integration problems, they can take the form of conflicts, right? So for example, cruise control and collision avoidance might conflict over what they want the speed of the car to be, right? And so there's going to have to be some glue code that figures out what really ought to happen. Whereas the feature interaction that we saw earlier with running the YouTube in PowerPoint on a Mac connected to a data projector, well, somewhere along the way, one of those features violated an assumption of another feature that would actually disallow me from playing the video directly in presenter view mode. So just a couple of examples. We've got users who have different features as part of their cell phone. So we've got Anne and Pat who both have voicemail feature that allows someone who's calling them to leave a message if their call doesn't go through. Pat forwards calls that she gets to Anna because maybe she is away for the day. And what happens if the call attempt fails? Right? So Sal calls Pat, Pat calls Anna, the call fails. Some voicemail service should take a message. Well, which one? Both of them? Probably not. Anna, that's the easiest one, it's right there. Pat, she was the one who was originally called. So these are some of the questions about, yes, there's an interaction, how do we want to be resolving it? And does your answer change in a different context? So for example, if Pat's number is instead a number to a group, a sales group, and numbers to the sales group are forwarded to all of the sales representatives, and a sales representative doesn't answer, maybe we want the sales group number to take the message, right? So that it does reach some representative in the group as opposed to just waiting for Anna to come back. In a different context, what if Pat's on a long leave? Right? If Pat's on a long leave and the voicemail is left on Pat's voicemail service, then it might be a long time before it's actually answered. Different example, cruise control. So we've got two features, cruise control and traction control. Cruise control maintains the speed of a vehicle to a set value, what the driver wants. Traction control helps to regain control of the vehicle if the wheels start to slip. So if you're on ice and your wheels start to slip, traction control will put some brake pressure on the wheel to slow it down so that it regains traction. Okay, so what happens if they're executing at the same time? Well, traction control is going to apply the brake to the slipping wheel, right, to get it to slow down. That's going to slow down the car, right? And so the cruise control is going to want to speed up the car to get it to maintain speed. There is glue code in the program that says that traction control should have priority here, which is good because traction control is a safety feature. But in the meantime, cruise control is revving up the engine, trying to maintain speed. And so once traction control does effectively regain control of the car, then it stops doing that, and the driver senses this sudden acceleration because the engine power has been increased and difficult to control. Okay, so what's the resolution to this one? I can promise you that if you go home and look at the user manual of your vehicle, it says do not use cruise control on slippery roads. Okay. So in all of these cases, the features work as advertised. They work as specified. There's nothing wrong with the individual features, right? It's just this overall coordination of how features need to work in combination. And in fact, you should be thinking about it in terms of these features having additional requirements, additional functionality of what happens in these other situations. You should almost be thinking about them in terms of, there's some basic functionality, right? At the top, cruise control has this basic, nice, logical, cohesive functionality. And then it's got all these extra clauses about how it behaves in situations of the existence of other features. Okay, and this style is okay, except that if you have lots of interactions, then there's quite a number of exceptions, right? So if you've got a situation where not only, we did a study with the telephony features, features may have lots of interactions with lots of other features, but even between the same feature, there may be lots of different interactions that all require resolutions. And so you get this death by exceptions, right? Where the development of a new feature, a nice, simple, cohesive feature, is actually dominated completely by all of the work that it takes to detect interactions, fix them, and test them. So what is research trying to do? We're trying to do two things. We want to help detect interactions, and then also talk very briefly about resolving interactions at runtime. Okay, so detection of interactions. This work comes out of the Wattform group, the Waterloo Formal Methods. The group itself focuses on using mathematics to model and reason about computer systems. Most of this work is for the purpose of ensuring that software is acceptable. And so by model, it can be models of structure, models of software structure, models of rich data. It can be executable models in terms of how the software is supposed to behave, how it's supposed to react to inputs. It can be properties about the software, so just declarations of properties, and these tend to be expressed in logics and constraint languages. Okay, so this problem of feature interaction can be expressed as a math problem, right? So if I take a feature of interest and I write an executable model of that feature, I don't think that works. I write an executable model of that feature in terms of how it reacts to inputs, such as call screening, right? So I might have a model of a call screening feature that when an incoming call comes in, it compares the number of the caller to an address list of forbidden callers, and it terminates the call if the caller is on this list. And I've got some properties of features, such as for call screening, I don't want a connection between anyone on this list and the subscriber. Then it should be the case that the model satisfies this property. Okay? And if I do that with a collection of features, build an executable model and demonstrate that those executable models satisfy their respective property, then feature interaction occurs when we take all those executable models, compose them together into a product, and test whether they together satisfy the collection of the features properties, and that proof doesn't hold. So there's very nice technology called model checking, which will do effectively an exhaustive search of the execution paths through an executable model and test whether properties hold. Okay, that's a very oversimplification of what a model checker does, but you can think of it in terms of how we started off with is you can't do an exhaustive testing of the software. Well, it effectively does exactly that, right? It does an exhaustive search of all the possible executions through the software model, and it comes back with a yes or no. Yes, success. The model actually satisfies the property, or it comes back with a no, and here is an execution path that violates the property. Okay, so we have used this on fairly large examples. The most notable one was when we applied this to the requirements model of a US naval aircraft. It had 3 large features, so these are more subsystems than features. Navigation, which sort of computed the airplane's current location. Navigation update, and so it would occasionally recompute its location based on some external reference, right? So instead of relying on its internal understanding of where it is, it would reestablish a good understanding of where it's located. And then weapon delivery, right? So targeting and dropping and releasing weapons on targets. And it also had a collection of properties which mostly had to do with legal mode combinations, right? If the system is in a particular mode in navigation, it shouldn't be in a particular mode in weapon delivery. So this kind of property is perfect for model checking, right? Because no human's going to want to go through these 3 large software models and try to figure out what are, which of the combinations of modes are actually reachable. So, and in fact, when people did try to do that, they made mistakes, right? There was, a simple property that was thought to be false, but when we ran it through the model checker, it was actually true. It was not possible. But this property turned out to be false, right? So this property said, if the navigation subsystem doesn't know where it is, doesn't know where the aircraft is, right? There's sensor failures, and so all of its calculations are based on stale data. The navigation system doesn't know where the aircraft is, then the weapon delivery mode should not be in a mode where it is dropping, targeting, dropping targets, or dropping weapons on targets, where the target's location is based on the aircraft's location, right? And this turned out to be false. Okay, so it sounds very simple. What are the real research problems, right? It's supposed to be push button verification. What are the real research problems here? A lot of the research goes into how to make this model checking algorithm reasonably efficient, right? So I explained it in terms of an exhaustive search, but that's not exactly how it is how it's done. Right, so what kind of representations of the model, what kind of algorithms can we re-express the problem into a simpler problem that is more easily solved? We've done a little bit of work along these lines, but not a lot. For the most part, we've been users of model checkers. The kind of work that we've been focusing on have been in terms of the software model and the property, right? So how can we create abstractions, really aggressive abstractions of the software model to reduce the size of the model that we're feeding to the model checker, because model checking is a complicated verification process, and anything we can do to reduce the size of the verification problem is a win. We've focused on composing software models. We want to support this notion of feature decomposition, but that means we have to be able to take models of features and compose them together into a model that represents the collection of features. We've done a lot of work on easing the task of creating models and writing properties, right? Because these are, at the base, they tend to be mathematical models, right? And so how do we use them? How do we have different other languages or patterns or automation to ease the task of actually creating them, so that you don't have to have a PhD in order to use this technology. And then also looking at improving the output of these tools. Okay, the detection of interactions works well if you know all the features that you're working with. Right? If you're a company that is developing a product, you probably know all the features that are going to go into that product. But increasingly, companies are assembling products out of components that they're getting from other sources. Or users and consumers are buying and assembling and interconnecting products from different vendors. And in those cases, it's not really possible to know in advance what all the features are going to be to do any kind of automated detection of interactions. And so I'm going to speed up. So for those, we really need to be looking at runtime resolution of interactions. And it would be common normally to have some kind of an arbitrator that would take the actions that features want to apply, decide how to resolve interactions, and then pose the interactions to the actual actuators. And that only works if you have the ability to have some kind of a centralized arbitrator. But in a system of systems, there really isn't a centralized authority that can host an arbitrator. So some of the work that we're doing here now, currently, is looking at, well, how can we take that arbitration process and distribute it among the components of a system of systems. Some of the theories that we're working on now is, decomposing this arbiter in terms of, well, what are the actions that they're trying to arbitrate? They tend to be associated with a particular, output device or actuator or output variable. So, let's associate the actuators with those and co-locate the actuators with those, the arbiters with those actuators, right? So now what the process looks like is a feature gets input from sensors or what have you. It sends what it wants to do to the various arbitrators depending on what its outputs were going to affect. The arbitrators per actuator will do local resolution and then pass that on to the actuator. So this has nice properties in the sense that the arbiters are co-located with the actuator that's going to be affected. The arbiters are feature agnostic in the sense that they can't know which features they're arbitrating, right? Because features can come and go. The products that the users can come and go. And so instead, all the arbiters know is that they're getting actions, and then they're arbitrating among the actions. And the arbiters themselves can have actuator-specific resolutions, which can be important. Okay, and we're in the process of testing this with automotive software. So we've got implementations that are currently working in simulation and working well in simulation. We've gone through the process of doing mathematical proofs that the arbiters make good decisions given a set of conflicting actions. We've gone through simulations to make sure that, given a sequence of inputs, they actually come up with a good sequence of resolutions. And then now we're interested in, can they do this in real time? So I apologize for the speed at which the last part of the lecture was given, but I hope that some of the takeaways are that, yes, right now, using current technologies, it is impossible to write error-free code. And I think it's going to continue to be impossible if all we ever look at is testing. So starting to look at mathematical models and mathematical reasoning to be able to reason about the existence of errors. And that's possible if you know all the pieces of your product in advance. And if you don't, looking for strategies for how to resolve at runtime some of those errors. So thank you very much.
Thank you, Joanne. Absolutely fascinating.
Thank you.
In terms of the potential, but also sobering.
Yes, it is.
In the context that there's no such thing as error-free software.
Right. And now you know why the verification researchers will not fly on fly-by-wire aircraft.
Yeah, exactly. This talk is now open for discussion, and once again, I have to remind you that this event is being webcast, and in order to capture the discussion fully on the webcast, those of you in the audience who pose questions and otherwise contribute to the discussion do need to use a microphone. And Sabrina has a microphone?
No, you have the microphone.
I have the microphone. So she's going to move this microphone around as you raise your hands to participate.
Thanks. I understand there's an old saying that software is never finished, it's only released. And I wonder about how companies make the decision as to cost-benefit analysis of continued debugging. When is enough? When is good enough? And how much more does it cost? This is a sort of corollary question. How much more does it cost to get that extra order of magnitude that NASA achieves?
So those are very different questions. Yeah. So you're right. The style of releases is changing radically, right? In the sense, like it used to be, software would be released. It would be in a box that you would go to a store and buy. Some software these days, it's simply available and is updated without you even thinking about it. And so in that mode, with this continual release, continual deployment model, we're actually seeing less testing. And we're actually seeing less testing by the developers and more testing by the users, right? And what companies will do is they'll release it to a very small market. And if they get problems, then they can pull it back and fix it. And if they don't get problems, then they can gradually increase the market. So when it comes to testing of software that's sort of available online, you'll find that we are doing much more of the testing. That's not going to be the case of more enterprise software, business-to-business software. With respect to how much more costly it is to gain this order of magnitude improvement, I don't know the answer. If I had to guess, I would say it was an order of magnitude more expensive, right? The organizations that deploy those, they tend not to have time limits, right? These are military, it's NASA, it's aircraft company. They tend not to have time limits. They tend to have fewer budget constraints that other companies have, right? They tend to have government funding.
Okay, other questions?
Thank you very much for your talk. It's really interesting. I had one question about the resolving interactions at runtime. And I was wondering, why do you consider the interactions only on runtime, or what is the difference? Would that be possible if we consider all the possible interactions before the runtime, and how does that make a difference?
Right. So you would do this if you couldn't consider them all in advance, right? So the talk about the model checking is one strategy for detecting interactions in advance, and all it does is detect them, right? It still means that the user or the engineer needs to go off and develop analyze it, see whether it's an undesirable interaction, develop a fix if it's not. The runtime interaction is recognizing the fact that there are going to be cases where you don't know all the features ahead of time, and so you can't do the analysis if you don't know all the features. So for example, in a system of systems, where let's say you've got your smart car, and the driver is connecting a bunch of smart devices into that car, right? It's got a smart car seat, it's got some cameras, it's got a smart windshield wipers, it's got a phone that's connected to Wi-Fi. Some of these products might be invented and integrated, they might be invented after the car has been released. They're certainly going to be integrated, aftermarket if the car is released. There's no way to test all of these in advance. And so, when you start talking about connected products, when you start talking about Internet of Things, you need the ability at runtime to detect and resolve interactions, even if the resolution isn't, the perfect resolution that you would do if you were to resolve it in-house.
Okay, thank you. Other questions, comments? So Joanne, I'm fascinated about the relationship, to the extent that it exists, between software code and the way the brain works. So you've convinced me today, very clearly, that there's no such thing as error-free software code.
Right.
And I know from my own experience that my brain is buggy. Every time
That's right.
I'm reminded of
That's
this,
exactly
every time
right.
I forget to take flowers
That's
for my wife
exactly
on her
right.
birthday.
That's exactly right.
So,
That's exactly
so my
right.
question to you is it possible down the road given the fact that there's no such thing as error-free software, that it will be possible to fully simulate brain function using software development?
So that's a question for an artificial intelligence person. And my guess is that's not the direction that they're going to go in. But I would, a lot of the learning that is going on, for example, learning of the world models, is effectively, simulating the humans learning, processing. I would also say that you're right. The human brain is buggy. The software is buggy. In some cases, the human brain is buggier, and you want to rely on the software. And in other cases, the software is buggier. So for example, like I said, verification people tend to worry about getting on aircraft that are fly-by-wire, right, where all the controls are software controls. There seems to be less trepidation about automated driving. And that's partly because in the cockpit, you've got an expert driving piloting the aircraft, and B, if there's an error, there's not a whole lot way of recovery, right? You are going, if you're going to drop from the sky, no one's going to survive. But in the car, human drivers are not that good. The average human driver is not that great, and so the automated software may actually be better. And in fact, there is already software in your vehicle that overrides the driver, right? All of the stability control software, the traction control software, anti-lock braking, those are all software features that override the human driver actions. So we already are living with some software in our cars that are effectively driving the car for us and in fact correcting the errors that we make.
Okay. Thank you. Other comments and questions? Anyone? Okay, well, please join me, ladies and gentlemen, in thanking Joanne for an absolutely fascinating presentation.
Thank you very much.
We really appreciate it. Thank you very much indeed. And I'd like to take this opportunity to remind you that the next research talks session or lecture will take place on March the 24th, and it will feature Professor Karim from the Department of Electrical and Computer Engineering. So please keep your eyes open for that. And once again, thank you, Joanne.
Thank you.
Really enjoyed it.
Thank you.
Thanks. Absolutely fascinating. Absolutely fascinating. Absolutely fascinating. Absolutely fascinating.